It's that time. So today we're finishing up UML stuff. I think we can probably finish it today. You'll be getting your first lab in this class probably today or tomorrow. But you should be focusing on the exam before the exam on Friday. Beyond that, does anyone have any questions about the study guide? We will be spending tomorrow's class doing review. I received one request for some examples of the begin function in JUnit to see how that works. Does anyone else have anything they'd like to add to that? All right, do your best to come up with 4 or 5 questions or things that you are uncertain about, would like some additional examples of. Other than that, I will just be coming up with answers to your questions off the top of my head. So I think that should be reasonable. If we end up with a dearth of questions, then I will set you free to study. And we'll take the exam on Friday. So this is the last week or last day's worth of content before next week. Questions or concerns about the upcoming schedule, what to expect for the exam?
When did Jeff take place over the class period, I guess?
Yeah, it's gonna be during Friday's class for the exam. Yeah, so we'll only have the hour. I usually give people the 10 minutes between classes afterwards, so you have up to 60 minutes. And remember that if you have any accommodations, those are not, they don't happen automatically. That's something that you need to talk to me about. So if that is the case, please do let me know that you would like to use them. And of course, I can work with you on that, try to find you a room, whatever it is that you have accommodations for, I can help you with that. Last time we talked about different relationship types. I wanted to cover those again really briefly, just to make sure that they are clear. So we started by talking about association. Undirected association just said there's no directionality to the relationship. It's just saying that these two classes are related in some way, but not in a way that's definable by these other types of relationships. So between an airline and an airplane passenger was the example that we used here, as they're related, but they're not really specifically related. There's just, they have to do with each other somehow. So we can specify that with this block arrow. There's no real arrow, it's just a connection between the two classes. There was directed association, where if we have a container and some containees, like an airplane contains passengers, then we draw an arrow from the container to the containees. Again, we're not specifying exactly what type of relationship this is. They're just associated with each other in some capacity, and we have a container and some containees. Reflexive association has only a single class. It's a relationship between a class and itself. We also talked about multiplicity, talking about how to specify that there may be 0 or more, or 1 or more. You can use this ... star, or just star to represent the closure of it, basically. That means 0 or more. We talked about other multiplicity, where an airplane can have multiple passengers. It can also have 0 passengers. So that tells us that an airplane worked by itself doesn't need passengers, but there could be an arbitrary number of passengers of a single airplane. We talked about the big difference between aggregation and composition. This is a very important difference because it's very commonly confused. Both associations mean that a class belongs to a collection, but one implies ownership, whereas the other does not. So composition implies ownership, aggregation does not imply ownership. We had a couple of examples. A car owns its wheels, a project doesn't own its consultants. So we had composition in the car's position and the aggregation of the projects position. We also talked about another example of this class and students and the Catalyst building and classrooms. The composition of this in this case was that the building owns its classroom. We can't have a classroom that belongs to multiple buildings, whereas a student can be taking multiple different classes at the same time. So the class does not own its student. We looked at some examples of this in code and tried to compare what happens if we have composition on the left and aggregation on the right. If a car owns its engine, then an engine belongs to a car. You can't swap them out. So they were final on the left, not final on the right. When you construct a car, we either set the engine to be an engine that's passed in, or we make an engine and immediately attach it to the car. So a car cannot exist without an engine, and the engine cannot be moved between cars. It is part of the car. When the car moves, on the left, a car can't exist without an engine, so we can just say, engine that we know exists, make the car go vroom. And on the right, we have to check if it's null because we don't know whether this car has an engine or not. It's possible for a car to exist without an engine, so we need to verify that there is an engine before we press the gas, if we expect the car to go forward. We talked about generalization, which is our name for an inheritance relationship. This has the open triangle. We have an abstract class or an interface up top, and we have concrete classes at the bottom. Although we can, of course, have relationships between abstract classes as well. So a hospital doctor is an abstract class that extends the doctor abstract class or interface. So this can be arbitrarily complicated. Realization was this idea that in order to use a printer, the printer needs to be set up. So if we have a class for the printer setup that says that unless that has been interacted with in some regard, we can't use the printer. So the printer is the implementation of the functionality defined in the printer setup. If you want to know how or why a printer works, look at the printer setup. So we are now going into the rest of the different types of diagrams. And we're going to start looking at what are these other kinds of diagrams? What can they explain with regards to a coding problem? You can also have the difference between high-level diagrams and low-level diagrams. High-level diagrams don't really give us any of the fields or methods associated. They just really show the relationships and highlight the relationships between classes. So this tells us that a project is made up of one or more activities, an activity is made up of one or more tasks, and a task can be assigned to a resource. Each task has a resource, but a resource could have an arbitrary number of tasks. Tasks are split among multiple resources. And we glean all of that from just this image. We can have lower level or more detailed class diagrams that tell us, all right, what is a project composed of? What are those fields and methods? What do those methods return? All of that information is now shown to us in the detailed class diagram. But notice how the relationships now kind of take a back seat to the structure of each of these. So think a lot if you're designing a UML about what do you want the takeaway from this UML to be. If you want it to be something that is high level, then you should make a high level diagram that highlights the relationships. If you want it to be a full specification and resource for people who are implementing the code, then maybe you want to design something more detailed like this. This would be much more useful to a programmer to make sure that when we make the activity class, we have the associated and appropriate fields and methods implemented. Whereas if we're trying to communicate this with a client, they don't want to see this. They don't want to know all of the internals of exactly how it works quite as much. Maybe this makes more sense as to what to show the client to say, yeah, that seems like the system that I would like you to design. We can also detail some more of these. So activities and tasks themselves can be worked on. So we can now show the inheritance relationship, which we see with the open triangle, between the fact that activities and tasks are workable or work effort. Questions on different abstractions of class diagrams? All right, the next thing we might want to look at is an object diagram. So while a class diagram describes the blueprint, the thing that you would write into the code, an object diagram shows an actual instantiation of an object. So now instead of the blueprint for a phone, you're actually showing one of these phone objects. So think of this like a snapshot in time. In the middle of the operation of this project, what does the internals of the system look like right now? An example of this would look something like this. So now we have this ongoing project. So in human resources, we have system development. We have a project ongoing that is the human resource system development. And as a description, this is our project and a start date that was probably before most of you were born. We have activity scopes. We have tasks. Both of those are of type scope. We have more tasks, a review that's ongoing, an activity that's ongoing, a design task, an analysis task, an implementation activity, a code task, a test task, and a deployment task. Note that these are all instantiations of the tasks and activities that we described in general on the previous few slides. But now it represents kind of a snapshot in time of what are the ongoing tasks and activities and how do those classes that are instantiated relate to each other. In a design process, you will often find yourself doing something like this, where you say, here's an example of when you're using our software, here's an example of what the internals of it might look like as you are using it. That can be very useful from a client's perspective who wants to eventually be using this system. If you haven't implemented the system yet, this would show your client what it is like to use the system. It's nice to have a visual way to see how do all of the components of the project relate to each other. Note that we can also have some invalid object diagrams. Do we know what's invalid about this based off of the descriptions from before?
What says on the top, maybe, like it says payroll. That kind of says.
It's actually this connection right here that can't exist. If we look back at the specification, a task can't compose an activity composes a task. So it's very difficult to make sure that it's perfectly right. And of course, you can have object diagrams that don't adhere to the rules that you have specified. And those can be very difficult to spot. So those are object diagrams. Again, they're instantiations of objects, kind of a snapshot of your project in time. The next thing we might care to write out is a sequence diagram. When we talk about use cases here, what we mean by this is in software engineering, we have lots of different people who want to interact with a system maybe in different ways. So we would have a use case from the system administrator who wants to make sure that the system remains online. The use case of the client or the user who is trying to use the system. The use case of the business who wants to ensure that they're profitable. And that using this system allows for some kind of bottom line of profit. There are lots of ways that we might care to look through the lens at a system that we are developing. So sequence diagrams allow us to look at what happens when we use the system. So something like, if I am on the home page and I click on this link, then I end up on this page. That is a sequence of actions. If I were to kind of write a unit test for the using of an application, you could pretend to sit in front of this application and play around with it. You click on something, end up somewhere, click the back button, end up back where you started, submit some information, see that you're authenticated. So you can map the sequence of those actions and show how the system evolves over time as someone uses the system. So rather than being a snapshot in time, now we want the flow of the diagram to show some kind of sequence of time or sequence of communication or calls between the different pieces of this project. Let's say, for instance, you want to query your account balance in your bank. There are lots of servers that store lots of different information. There are valid ways for those different servers to communicate with each other, but only if they're appropriately authenticated. A sequence diagram would show something like, what is the sequence of calls that needs to be made before the person who initiated the request, what is the balance of my bank account, sees the balance of their bank account. Because I should not be able to see the balance of your bank account. So we have things that we might want to concern ourselves with sequence diagrams, like the roles of all of the classes. What is the purpose of them? When do they live? So the lifelines, when is an object instantiated? When is an object destroyed? How long is it going to be alive? Should it be alive after something like my query for the account balance goes away? Should my account exist after my query for an account balance? I would hope so. How much money do I have? Great, but now it's gone. So we can look at activations and messages as well. What are the actual communication between objects? Where do those objects live? So we are going to look at, as an example, querying the balance of an account. So we have the bank object, we have the account ledger object, and we have the checking account object. So the client on the very left does something that invokes the getBalance method. A parameter to this is the account number for the balance that they want to get. This goes to the bank object. The bank object receives the query for the balance. Before we access the checking account, we should go retrieve the account, because the bank is not going to store the account. The account ledger is going to be where the account lives. So the bank is going to take that balance request and turn it into a request to return the object that is the account in question. So it's going to convert that into the associated request. It's going to get the account back from the account ledger. Once it has that associated account temporarily, then it can actually get the balance query online. So we can now query the checking account, which is one of the many accounts in this account. So we can go find the associated account and get the balance of it, returning the balance from the checking account, which then gets returned to the client. And we note that at the end of this, the account from the bank's perspective has been destroyed, but the account still exists in the account ledger where it could go be retrieved again on an as-needed basis, for instance, if the user immediately again queried for their balance. That way we have an appropriate separation of concerns. But now we also see the sequence of calls and the associated objects for those calls to be able to do something like how does the get balance work from the client's perspective? What does it actually look like in the internals of the system? Questions on how this communicates a sequence of events. Here's another example. You're sitting using the Outlook desktop application and you click the check email or refresh your inbox. The very first thing that it used to do was send all unsent emails. So your machine will send any unsent emails and send that request to the server. Then it will send a query to the server for, are there any new messages that I need to display? It waits for a response, yes or no. If yes, then it sends the request to download all of those emails so that you can see them. And then maybe it sends a request to delete any old emails that you don't need anymore. Maybe this is how we would prefer to make an email application. Very old-fashioned. But it allows you to see exactly how the communication worked between the client and the server. What calls are being done? When are we waiting for a response? If you're a programmer, this helps you to make sure that you have the functionality complete. If you're the client, it tells you, what do I need to do? One more example. We'll go back to our projects, activities, and tasks. The project manager wants to remove a project now. Unfortunately, a project may contain many activities, and those activities may all contain many tasks. So if we just want to remove a project, we want to just click the Remove Project button, but the underlying logic for this may be significantly more complicated. We need to identify all of the activities that belong to the project and all of the tasks that belong to each of those activities. In data structures, we just talked about recursion. This is a very good example of a recursive algorithm where we might want to say something like, look at all of the activities in this project and continue this process until there are none left. So the project manager sends on the remove project. From the UI, we need to find the project. So we're going to go search for the project, return the project. We then need to, for that project, identify all of the activities that are in that project. For each of those activities, we're going to need to find all of the tasks that are associated with that activity, remove all of those tasks until there are no more tasks in that activity. Then we can remove the activity, continue that process until there are no more activities, and then we can finally remove the project. If we just remove the project without removing the activities and the tasks, those are going to continue to live on without having any way to access them anymore. Maybe we get some kind of memory error, out of memory error eventually, if we fail to implement removing a project by removing its underlying activities and tasks. An example of this might be something like this. This shows a more in-depth example of exactly how this would work given some kind of project. So we'll find the project Human Resource System Development. Then we will find the first activity, which is the scope. Within scope, there is a review task. There is a scope task. Once we remove both of those, we can finally remove the scope activity. Then we find the second activity, analysis design. We can then find all of the tasks that are associated with that and remove them. And again, we have an image that represents the logical process of how do we remove a project. Questions on any of the sequence diagrams examples that we've gone over? Truly thrilling stuff. All right, activity diagrams. This can show it's kind of like a sequence diagram, but it shows how the entire system is affected by some kind of activity. So it's very similar to a flow chart, and it will also use a lot of flowchart symbols. Here's an example. we are an online ordering system. And eventually we receive an order that needs to be fulfilled. There are two different departments that need to handle this request for an order. There is the payment or accounting, whatever you want to call the right-hand side of this, that deals with the money. And then there's, of course, the logistics side of it that needs to fill the order and make sure that it gets delivered. So when we receive the order, two different orders go out, one to each of these departments. And we can work on these simultaneously, is what this is telling us. The flowchart is saying that we can be filling the order at the same time that we send the invoice. There are different people responsible for each one of these. So we can fill the order and send the invoice, but we don't want to receive payment before we have sent the invoice. So once the invoice has been sent, then we can fulfill the payment. Once the order has been filled, then we can figure out, is it an overnight delivery or a regular delivery? So we have forks versus branches, and we have ways that we can show branches, ways that we can show forks and joins. Once the overnight delivery or regular delivery has been organized, then we merge that logic together to say, regardless of what was done here, we can now continue with our logic. Once payment has been received and the order has been shipped, then we can join this, and only then do we close the order. Only once both payment has been received and we have gone through the delivery process. This also allows us to do things like segregate these by the associated department that is responsible for each of these tasks. And this can tell us when to do something. So if we are a member of customer service, we receive the order, we are responsible for sending the invoice and then notifying finance that we've sent the invoice. It tells us when do we need to act and who do we need to communicate with after each of these processes are done. To close the order, we need to hear back from both finance about payment and fulfillment about the order status, the delivery status. Once we hear back from both of those, then we can click the button that closes the order. So all of this tells us how to work from the customer service perspective. It also works from the finance perspective or the fulfillment perspective. You could even have different sub-diagrams that are involved in your diagram. So for instance, now we can put a box around all of the delivery logic. And we see that the delivery logic itself is its own diagram that has a beginning and an end. So this usually defines here the beginning of a process, and this is the end of a process. So this is a sub-process within our overall process. So this helps us to be able to see that. I can't stress enough the importance of being able to visually represent your project, because most people are visual in nature. And so it's necessary to be, if there's any communication to be done with your project, there's always communication to be done with your project, to have visuals that represent that. Let's think about an example here. So we have the following situation. We need to accept payment and send an order to a warehouse to be delivered. The warehouse throws an exception to denote that the product is not available. We then need to back charge the credit card so that we can put money back on it because exceptions. How would you want to be able to show or handle exceptions in a visual manner? How could we change the images on the prior screen to show something like something went wrong? Yeah?
So should there be another communication between this delivery process back to the customer service? So they can show or kind of give feedback, hey, I don't have this. What do you want me to do now?
Yeah, we need some way to cancel the order in here as well. And it's probably customer service. We need to send some kind of email explaining what went on. Delivery should cancel what they are doing and not actually try to ship a product that doesn't exist. We don't want an empty box appearing at the eventual destination with nothing in it. That is going to be an unnecessary cost.
Could you just add in another communication, right, I guess right before the received order to do like a check stop?
Yeah,
See if it has it in inventory just to start out with, before you even place the order in.
do we want to incorporate it into this same diagram? Should we have this is how the order usually works, and here's how an order works if things are not canceled or if things don't work? So you can do something like this. There's an interruptible activity region that you can have with dashed lines that show maybe something happens. But note that once the order is closed, we don't want the ability to cancel the order anymore. It would be very nice from our perspective if we order something from Amazon, Amazon ships it, and then you say, cancel, I want a refund. You get the refund and you get the product. That sounds nice from the end user's perspective, but if you're designing a system for a company that wants to be able to fulfill this, then that would be a horrible breach of their business model. So you can define something like an interruptible activity region that says a cancel request is very much allowed as long as we are currently in this dashed line part of the flow of this system. Once we are outside of that dashed line, we cannot cancel the request anymore. Once we've closed the order, then we cannot order a cancellation. We would have to order a return or something that has a different process than the cancellation. This would just be for, I ordered something, it hasn't been shipped yet, please don't ship it to me and refund me. So activity diagrams also show this. We end up with, again, these lanes of fulfillment, customer service, or finance. We can call them swim lanes if we want, because they look kind of like swim lanes in a swimming pool. We have action states where an algorithm is actively doing something. Action flows where we show the relationship between different objects as they are communicating and performing some kind of action. We also have the concept of object flow, where how are objects being utilized as this action is happening? So are objects being instantiated, created, destroyed, communicated with each other, duplicated? All of this logic can be embedded inside of the UML in a way that helps to be able to add clarity to the systems. Finally, we have state chart diagrams. If you've never heard the term automata before, you will hear it a lot by the time you are done with the major. But you can think of it like a state diagram. We need to know the internal state of something as well as how that internal state can change. An example to this would be something like a button. A button's state is either on or off. If you push a button that is off and hold it down, then it is on. If you release that while it is on, then it is off. And this specifies both states of the button as well as how those states can change. What action is required such that the state of this object changes. And this can get significantly more complicated than an individual button, but it helps the idea of keeping it as simple as possible between on and off and what happens to change that. We will find that computers are really just complicated state machines like this. If you're curious about exactly how to model a computer with a system like this, take compilers from me. I think it's going to end up being required for most of you, but it is very exciting to just see how computers are structured like this. Another example for this, for a state diagram, is we have either a resource that is not assigned or is assigned. In order for a not assigned resource to become assigned, it needs to be assigned to a task, and we need to increment the number of assigned tasks. We actually go through that assignment process, and then we have defined what it means for the state of this resource to go from not assigned to assigned. Something that is assigned stays assigned unless it is unassigned from that task. Once that happens, then we can transition back from the state being assigned to the state being not assigned. As we do this, we find that the resource that was being used on that is now idle. So the task is either not assigned or assigned, not assigned, assigned. You can assign it or free it. And again, it just shows exactly how that process works. Here is a state diagram for the use of a beer mug. It starts out being clean and empty. If someone orders a beer, then the clean, empty mug becomes full of liquid and is now dedicated to be in service. Once it is in service, eventually the customer will drink the beer. As they do so, the cup becomes empty again, but it's still in service. If it's in service and empty, the customer can now reorder another beer, which means that it contains liquid again and is still in service. But if the customer declines, saying, I'm good, no more drink, then we transition to a state called dirty, where it needs to be washed before it is clean and empty. And this kind of describes the life cycle of a mug. So there are two important variables here. It either contains liquid or is empty, and is either in service or is not in service. And I guess it's either clean or dirty. So three variables all being shown in terms of the states and the transitions between those states and the associated logic that needs to happen in order for those transitions to take place. So we can show any amount of logic really by talking about them as states and transitions between states. And as you learn things like graphs in data structures or algorithms, then you're able to start envisioning these as a graph rather than as just a diagram. And then you can start applying any graph algorithms that you know onto these, and it'll all come together. Everything that you're learning in all of your different courses will come together and hopefully be useful. So stuff we covered. All sorts of different diagrams. Again, as I mentioned at the beginning of all of this, the ones that are most important for this class are going to be class diagrams. So we want to be able to go to Refactoring Guru and look at the design pattern UMLs and understand what classes exist as we're trying to code up these design patterns. But there are lots of other diagrams that will become more and more useful as you start taking classes like software engineering or your capstone, where you're producing large-scale projects in groups. There's more to UML. This is the most used subset of different diagrams. We should analyze it a little bit before we disperse, though. So what's good about UML? On the first hand, it's a common language. This means that we're all speaking the same language. If we all learn about UML together, then when one of us makes a UML, the others will be able to read and understand it. Visual syntax is good. A good picture is worth a lot of words. If you were to actually go back to any of the prior images and try to write out everything that was contained in that image, you would end up with a fairly long essay, probably. So good images can be worth a lot of words. And for those who are not technical, so your clients, it helps to be able to visualize what it is that you're going to implement for them. UML is not 100% precise, but to the extent that it is precise, you have to be clear about it. You have to understand your project to a level to be able to diagram it, which is much better than just thinking about how would I have described my project in words. And it creates something that's easier to go back to at that point. You can go back to something that you drew and refresh yourself a lot faster than natural language. It also becomes great for support if you are if you're managing a call center, for instance, and it's the IT call center for some support for some product. If everyone you hire has access to the same diagrams, then they can explain how things work visually and keep track of where they are in the problem-solving process as they talk to someone who's using your product. On the other hand, what's kind of bad about UML? Well, one, it is absolutely a hodgepodge of ideas. It's not one system. I kind of explained a bunch of different systems, and you can imagine that each of those different systems are useful in different situations, which means that if you want to fully document a large-scale product, you're going to need to make lots of different diagrams, and it's not easy to organize all of that. So you'll have to ask questions about who's going to be using this. From their perspective, what does all of this look like? And you might have different diagrams from different perspectives for the same call or the same process. Visual syntax doesn't really scale all that well. You'll have to have different diagrams with different levels of abstraction for the internals of how a system works, for looking at different systems placed next to each other, how different large systems communicate with each other. You may need multiple different images in order to really fully understand how a system and subsystem work together. And if you have a very large diagram or a ton of different diagrams about a product, then you don't really get much of an advantage over using natural language. If your product has 1,000 different pictures, then it's just as hard to understand as a 1,000-page technical document. So use all of that to decide when UML is useful, what you should include in your UML diagrams. Maybe you only want the subset of most common issues or the most common ways of visualizing. There's no right answer necessarily. It's something that you're going to have to learn and experience before you really have an understanding of when is it appropriate to make lots of different diagrams, or what are the most important diagrams to include. That said, UML is used everywhere. It's used by users of systems, by programmers to understand what they need to implement, by vendors to understand the process of fulfillment, for instance. So it's useful. It is the first standard, but also note that computer science is an incredibly fast-moving field. So whatever is happening today and is used today may be out of date in a year or two. So that said, understand it, but also be willing to work with it. Understand those weaknesses, think critically about those weaknesses. Maybe you'll have a better idea that becomes the next industry standard. Or maybe you're just going to develop the next piece of UML that gets incorporated into the already thousands of pieces of UML that you like to use, your friends like to use, and nobody else knows about. That's UML. Does anyone have any questions about any of the diagram types, uses, pros, cons? It's a very important topic, but it is very dry. Very difficult to make this exciting. I tried. With 5 minutes left, I don't know if I really want to dive into too much of the next major topic. I don't think that's going to work out well for us. So I think I can call class 5 minutes early if that's okay with people. We will start it on the next major design pattern next week. And I will assign your lab, that'll be due, I'll give you at least a week to work on it.
So doing the calendar is really outdated.
What in Canvas?
Like the product meetings from,
Oh, are there project due dates already in Canvas?
they're like way in the past.
Yeah, there should not be anything visible with regards to projects or project. due
Okay,
dates.
they're still great.
Yeah,
Like
there
the
should
thing,
be,
what, that March, like it's very obvious, the past.
yes. From my intention, there should be nothing up regarding any projects or anything to do.
They're obviously because they were due, but practically speaking, it doesn't really affect us.
Yeah,
Yeah.
I'll have a new project that may be linked to an old project that has an appropriate new name for this point.
There's some. Working.